So we're going to be working on Chapter 7, Lesson 1, Polynomial Functions. We're going to learn how to evaluate polynomial functions. We're going to learn how to identify general shapes of graphs of polynomial functions. So vocabulary to keep in mind is what is a polynomial in one variable? What's the degree of a polynomial? And what are leading coefficients? What's the polynomial function? And what is end behavior? Where are polynomial functions found in nature? If you look at a cross-section of a honeycomb, you see a pattern of hexagons. This pattern has one hexagon, surrounded by 6 more hexagons. Surrounding these is a third ring of 12 hexagons, and so on. The total number of hexagons in a honeycomb can be modeled by the function f of r equals 3r squared minus 3r plus 1, where r is the number of rings and f of r is the number of hexagons. So polynomial functions. Recall that a polynomial is a monomial or a sum of monomials. The expression 3r squared minus 3r plus 1 is a polynomial in one variable since it only contains one variable r. So here is the key concept. A polynomial in one variable. So a polynomial of degree n in one variable x is an expression of the form a sub 0 xn plus a sub 1 x to the power of n minus 1, and so on, where all the coefficients, where a sub 0, a sub 1, a sub n minus 2, a sub n, are all real numbers, okay? And n represents non-negative integers. So basically all the exponents are positive, and these are all real numbers, these leading coefficients. So here's an example of a polynomial in one variable, right? All the exponents are positive integers, all the leading coefficients are real numbers. So this would be an example of something that is a polynomial to the 5th degree because the highest exponent of the variable is 5, and coefficients of 3, 2, negative 5, positive 1, and positive 1. The degree of a polynomial is one variable, and one variable is the greatest exponent of its variable. The leading coefficient is the coefficient of the term with the highest degree. So let's look at a couple of examples. So the expression 9 is what's known as a constant because it only has a number and no variable. So this has a degree of 0 because since it has no variables, it would be like x to the 0 power, right? And its leading coefficient is 9. This is a linear expression, right? X minus 2 has two terms, right? X to the first power minus 2. So this is, since the variable, its highest exponent is 1, it has a degree of 1, and it's 1x, so it has a leading coefficient of 1. Here's a quadratic expression, right? Again, you notice that the highest exponent for the variable is 2, so it's got a degree of 2. And a leading coefficient of 3, right? So the leading coefficient is the number in the front of the term for the variable with the highest exponent. So a degree of 2, leading coefficient of 3. Here's a cubic expression, 4x to the third power minus 6. This has a degree of 3 and a leading coefficient of 4. Here's the general term for a polynomial. This would have an nth degree because n would be the highest exponent. And its leading coefficient is a sub 0, right? So whatever number is in front of the x to the nth power. So let's look at some examples here. Find the degree and leading coefficients. State the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. So if we look at A is a polynomial in one variable. We can clearly see that there is only one variable and it is a polynomial. The degree would be 4 because 4 is the highest exponent. And its leading coefficient is 7 because the term with the highest exponent has a number of 7 out in front. For B, well, this one, if you notice, does not have one variable. It has two variables. It has x and y. So this is not a polynomial in one variable because it contains two variables. C, 7x to the 6th minus 4x to the third plus 1 over x. This is technically not a polynomial because 1 over x would mean that I'm dividing by x. So that is not considered a polynomial because this would be like x to the negative first power, and we cannot have any variables with negative exponents. Let's look at D, 1/2 x squared plus 2x to the third minus x to the fifth. This is in fact a polynomial in one variable. We could rewrite it so it's in the power of x are in decreasing order. So we can write it like this. Again, this would tell me that the degree is 5 and it has a leading coefficient of -1 because it's -1x to the fifth. So D would be a degree of 5 with a leading coefficient of -1. A polynomial equation used to represent a function is called a polynomial function. For example, the equation f of x equals 4x squared minus 5x plus 2 is a quadratic polynomial function. And the equation p of x equals 2x to the third plus 4x squared minus 5x plus 7 is a cubic polynomial function. Other polynomial functions can be defined by the following general rule. So again, here is a polynomial function of degree n, and it can be described by an equation of the form p of x equals, and here is the generic form of a polynomial function listed, where again, a sub 0, a sub 1, and so on are just coefficients that represent real numbers. And n represents a non-negative integer, so again, this would be in decreasing order for the exponents. So this is an example, f of x equals 4x squared minus 3x plus 2. So again, the degree of the exponent would be 2. Its leading coefficient is 4. And if you know an element in the domain of any polynomial function, you can find the corresponding value in the range. Recall that f of 3 can be found by evaluating the function for x equals 3. So if I wanted to evaluate this function at 3, I would substitute x with 3 in its place and evaluate the expression. So let's look at this. Refer to the application at the beginning of the lesson where they want us to show that a polynomial function f of r equals 3r squared minus 3r plus 1 gives the total number of hexagons when r is 1, 2, and 3. So we're going to use the example from the beginning, right, and find the values of f of 1, f of 2, and f of 3. So all we're going to do for these is evaluate the f function where r is 1, where r is 2, and where r is 3. So let's look at the first one. So if I wanted to find f of 1, I would substitute r with 1 in its place. So again, you don't have to do anything to the left side of the equal sign, just the right side, and go ahead and evaluate. So 1 squared times 3 is 3, 3 times 1 is 3, and then 3 minus 3 plus 1 is 1. F of r, right? Again, we're going to do f of 2 now, so we're going to substitute r with 2. So we're going to do 3 times 2 squared. So we do 2 squared times 3, which is 12. 3 times 2 is 6. And then that's going to give me 7. And then finally, we're going to go ahead and use that same function and substitute 3 in its place so we can find f of 3. So 3 times 3 squared minus 3 times 3. So 3 squared is 9 times 3 is 27. 3 times 3 is 9. And then 27 minus 9 plus 1 is 19. So here, from this information, we know that the number of hexagons in the first ring is 1, the number of hexagons in the second ring is 6, and the number of hexagons in the third ring is 12. So the total number of hexagons with one ring is 1. With 2 rings, it would be 6 plus 1, or 7. With 3 rings, it would be 12 plus 6 plus 1, which would be 19. So these match the functional values for r equals 1, 2, and 3 respectively. So in part B, it wants us to find the total number of hexagons in a honeycomb with 12 rings. So again, we would take our function and go ahead and replace or substitute r with 12. So again, 3 times 12 squared minus 3 times 12 plus 1. So I would do 12 squared first times 3, which is 432. 3 times 12 is 36, and then I simplify it to 397. So this would tell me that there would be, so if this is ring 1, ring 2, ring 3, once I got to the 12th ring, it would total up 397 hexagons in a honeycomb. You can also evaluate functions for variables in algebraic expressions. So here they give us some examples. So find p of a squared if p of x equals x to the third plus 4x squared minus 5x. So here we're going to be substituting a squared in for x. So anywhere I see an x, I will substitute a squared in its place. So a squared to the third power plus 4a squared squared minus 5a squared. So again, all I have to do is evaluate the right side of the equal sign, nothing on the left. So a squared to the third power is going to be a to the sixth. 4a squared squared, well, a squared squared is a to the fourth. And 5a squared is just 5a squared. So this would be the expression that would allow me to express p of a squared. Now b requires a little bit more work. So it's asking me to find q of a plus 1 minus 2 times q of a if q of x equals x squared plus 3x plus 4. So the first step I could do to just kind of make it a little bit simpler is evaluate the first part where I'm going to just do q of a plus 1. So I'm going to substitute a plus 1 in for x. So I'll do that here. So I'm going to go ahead and evaluate, again, just the right side. So I know a plus 1 squared, that would be a plus 1 in parentheses times a plus 1 in parentheses. You could use the FOIL method. It would give me a squared plus 2a plus 1. And then 3 times a and 3 times 1 gives me 3a plus 3. And then I have this plus 4 here. And then I can go ahead and combine like terms. So 2a plus 3a is 5a, and then 1 plus 3 plus 4 is going to give me 8. So I would have a squared plus 5a plus 8. So that gives me the first part, but now I want to find the second part where it says 2 times q of a. So what I'm going to do is I'm going to go ahead and replace x with a, right, q of a, and then multiply that expression by 2. So again, here's q of x. So 2 times q of a, basically all I have to do is replace the a with in the x, and then multiply it all by 2. So 2a squared, 2 times 3 is 6a, and 2 times 4 is 8. So this would be representative of 2 times q of a. So now that I found this part, and I found this first part, I can just take the first expression that I found and subtract it from the second expression, or subtract the second expression from that one. So let's go ahead and evaluate that. So again, the first part minus the second part, so a squared plus 5a plus 8, minus all of the second part, 2a squared plus 6a plus 8. So again, notice how I put the parentheses there. And then I can go ahead and just distribute the negative into the second parentheses, and then go ahead and combine like terms again. So 1a squared minus 2a squared is negative 1a squared. Positive 5a minus 6a is negative 1a. And positive 8 minus 8 is 0. So it leaves me with just negative 1a squared minus a. So now we're going to talk about the graphs of polynomial functions. The general shapes of the graphs of several polynomial functions are shown below. These graphs show the maximum number of times the graph of each type of polynomial may intersect the x-axis. Recall that the x-coordinate of the point at which the graph intersects the x-axis is called the zero of a function. How does a degree compare to the maximum number of real zeros? So here we have a constant function with a degree of 0, a linear function with a degree of 1, a quadratic function with a degree of 2, and a cubic function with a degree of 3, a quadratic function with a degree of 4, and a quintic function with a degree of 5. So notice that the shapes of the graphs for even degree polynomial functions and odd degree polynomial functions. The degree and leading coefficient of a polynomial determine the graph's end behavior. So the end behavior is the behavior of the graph as x approaches positive infinity, which is represented by this symbol, or negative infinity, represented by this symbol. This is represented as x approaches positive infinity and as x approaches negative infinity. So here is how we determine end behavior of a polynomial. If the degree is even, you notice that the ends of the polynomial head in the same direction. And when it's odd, I'm going to go back. And when it's odd, they head in opposite directions on each end, right? So evens head in the same direction, odds head in opposite directions of each other. So if you have an even degree polynomial with a positive leading coefficient, it will be pointing up both ends, right? Both ends will head to positive infinity. So here, f of x will head to positive infinity, right? As x heads to negative infinity. So as x heads to negative infinity, f of x heads to positive infinity. F of x will head to positive infinity as well when x is going to positive infinity. So as x goes to positive infinity, f of x goes to positive infinity. So basically what this is saying is f of x, the function, heads in positive infinity in both directions as x goes to negative or positive infinity. Now when you deal with an odd degree polynomial with a positive leading coefficient, The left side of the function, as f of x heads to negative infinity as x goes to negative infinity. And to the right, f of x goes to positive infinity as x goes to positive infinity. And then if your even degree polynomial has a negative leading coefficient, it does the opposite. Both ends will head in the negative direction. So f of x will head to negative infinity as x goes to negative infinity. And f of x will also head to negative infinity when x goes to positive infinity. When you're dealing with an odd degree polynomial with a negative leading coefficient, the end behavior, the left side as f of x goes to positive infinity as x goes to negative infinity, and f of x goes to negative infinity as x goes to positive infinity. So f of x going to positive as x goes to negative, and f of x going to negative as x goes to positive. So it kind of does the opposite when the coefficients are opposite of each other. All right. So the graph of an even degree function may or may not intersect the x-axis, depending on its location in the coordinate plane. If it intersects the x-axis in two places, the function has two real zeros. If it does not intersect the x-axis, the roots of the related equation are imaginary and cannot be determined from the graph. If the graph is tangent to the x-axis, as shown above, there are two zeros that are the same number. The graph of an odd degree function always crosses the x-axis at least once, and thus the function always has at least one real zero. So let's take a look at this one. So here, the same is true for even degree functions. One exception is when the graph of f of x touches the x-axis. So the number of zeros an odd degree function may be less than the maximum by a multiple of 2. For example, the graph of the quintic function may only cross the x-axis 3 times. Just like here, it only crosses it 1, 2, 3, when it potentially could have crossed it 5 times. So here we're going to take a look at some examples where we have to describe the end behavior of the function, determine whether it represents an odd degree or even degree polynomial function, and state the number of real zeros. So for A, we can tell that the function heads to negative infinity as x goes to positive infinity, and f of x heads to negative infinity as x goes to negative infinity. So it's going to negative in both directions. Since both directions head in the same direction, that would tell me it's an even degree polynomial. And the number of real zeros, well, it only crosses the x-axis twice, so it has two real zeros. Let's look at B. So for B, f of x heads to positive infinity as x goes to positive infinity, and f of x heads to negative infinity as x goes to negative infinity. So each direction heads in opposite directions. So this is going to tell me that it is an odd degree polynomial function. And if I look, it only crosses the x-axis at one place, so it only has one real zero. And let's look at C now. So if I look at C and I want to describe the end behavior, both ends head to positive infinity. So f of x heads to positive infinity as x heads to positive infinity, and f of x heads to positive infinity as x goes to negative infinity, because it heads to positive infinity in both directions. So again, since both ends head in the same direction, this tells me it's an even degree polynomial. And when it's asked how many real zeros it has, well, it has no real zeros because it never crosses the x-axis. So therefore, no real zeros occur for this polynomial function. All right, thank you for watching. Let me know if you have any questions.